Okay, hi folks, welcome back to another look at some advanced higher physics past papers, and this time it's the turn of waves. That's the travelling wave equation and stationary waves, so let's have a look for a couple of questions on them from Mr. Davies, Advanced Higher Past Papers by Key Area, Interactive PDF. And there's the waves questions there. And we're going to have a look at 2017 question 9 and 2022 question 11. So starting off 2017, and it's question 9. And as usual, it's a good idea to have a go at the question yourself first and then come back once you're ready and you can see how we have done it. So here we go. A wave travelling along a string is represented by the relationship y equals 9.50 times 10 to the minus 4 sine 922t minus 4.50x. And we have to show that the frequency of the wave is 147 Hz. Now the general equation for a travelling wave is on your relationship sheet, and it looks like this. Y equals a sine 2 pi brackets ft minus x over lambda. So let's see how that compares to the relationship that we're given in the question. Well, the first thing to notice is there's no 2 pi outside the brackets. That means that 2 pi must have been multiplied inside the brackets. So it becomes y equals a sine 2 pi ft minus 2 pi x over lambda. And from our work on rotational motion, we know that 2 pi f is equal to omega. That's on your relationship sheet as well. Omega equals 2 pi f. So omega is equal to 922 as shown in the stem of the question. And therefore it's just a case of rearranging that to get f. F equals 922 divided by 2 pi. And that gives you the answer we're looking for of 147 Hz. And make sure you give your answer exactly as it was given in the question because it's a show question. Only 1 mark for that, and the 1 mark is for showing the 922 divided by 2 pi. And of course the answer as well. Okay, A part 2, determine the speed of the wave. Well, this looks like v equals f times lambda here. It's a 4 mark question, so we'll probably get something a wee bit extra to do as well. But let's start off with v equals f lambda. We know what f is, it's 147, and lambda we can get from the right hand side of this relationship here. The 2 pi over lambda must be equal to 4.5. If you look at the equation in the very first line of the question, it says 4.50x. Well, the 4.50 must be equal to 2 pi over lambda. And again, rearranging there. So lambda will be equal to 2 pi over 4.5. In fact, we can just sub that straight into our v equals f lambda relationship. And if you do that on your calculator, you'll get an answer of 205 meters per second. Let's have a look at the marking instructions for these 2 bits then. So 9a part 1, it's a show question but just for 1 mark. And the 1 mark was for showing that 922 equals 2 pi f. Therefore f is 147 Hz. And then 9a part 2, it's a 4 marker. The first mark was for identifying that 4.5 was equal to 2 pi over lambda. And then subbing that into a straightforward 3 mark v equals f times lambda question. And getting the final answer of 205 meters per second. Okay, on to 9 part A part 3. The wave loses energy as it travels along the string, and at one point the energy of the wave has decreased to 1/8 of its original value, and we have to calculate the amplitude of the wave at this point. Well, straight to your relationship sheet, and we've got the relationship that links energy and amplitude of a wave as E equals Ka squared. Or in other words, the energy divided by the amplitude squared at one point will be equal to the energy divided by the amplitude squared at another point. Now if the energy goes down to 1/8 of its original value, we can sub in the number 8 for the original energy and also sub in the original amplitude, which was 9.5 times 10 to the minus 4, and don't forget to square it. Then our new energy will be 1 divided by the new amplitude squared. Then if we rearrange that to try and find a2 squared, then that will be 9.5 times 10 to the minus 4 squared all over 8. And if you do that on your calculator, and don't forget to square root it, you'll get an answer for the new amplitude of 3.36 times 10 to the minus 4 metres. Watch your significant figures there. All the numbers in the question were the 3 sig figs. So my answer is the 3 sig figs as well. There's 9A part 3 in the marking instructions. 1 mark for the relationship, 1 mark for the substitution into the ratios, and 1 mark for the final answer with the correct units. Okay, still in question 9, this time part B. The speed of a wave on a string can also be described by the relationship V equals the square root of T over mu, where V is the speed of the wave, T is the tension in the string, and mu is the mass per unit length of the string. And to work out the mass per unit length of the string, that's just the total mass divided by the total length of the string. And we're told the string's got a length of 0.69 metres and a mass of 9.0 times 10 to the minus 3 kilograms, and the wave's travelling along the string with a speed of 203 metres per second. And we have to calculate the tension in the string. So let's write that relationship down again, and then we're going to square both sides to get rid of the square root side. So V squared equals T over mu, and rearrange it for T, so T equals mu V squared. And remember, mu is the mass per unit length, so we can substitute in for mu for m over L. So T equals m over L times V squared. And then we can substitute all the values in. So T is equal to 9 times 10 to the minus 3 divided by 0.69, that's the mass per unit length, times V squared, which is 203 squared. And if you do that on your calculator, gives you an answer for the tension of 540 newtons. Let's have a look at the MIs. That's one of these unfamiliar relationship questions. So no mark for the relationship, but 1 mark for realising that mu is the mass divided by the length, 2nd mark for all the substitutions, and the 3rd mark for the final answer with the correct units. And then in part C, when a string is fixed at both ends and plucked, a stationary wave is produced. And we have to explain briefly in terms of superposition how the stationary wave is produced. Well, the superposition of waves just means interference of waves, and we're looking for an answer that contains the word interference. So when a wave's travelling along the string and reaches one of the fixed points at the end, then the reflected wave will interfere with the incident wave and produce fixed regions of constructive and destructive interference, also known as antinodes and nodes. But notice in the marking instructions, all you have to say is that the reflected waves from each end interfere with each other. And in 9 part C part 2, if the string is vibrating at its fundamental frequency of 270 Hz and it produces a stationary wave pattern as shown in figure 9A, well, figure 9B shows the same string vibrating at a frequency called the 3rd harmonic. And we have to determine the frequency of that 3rd harmonic. Well, the wavelength is 3 times smaller, so the frequency will be 3 times greater for the same wave speed. So therefore the frequency will be 3 times the fundamental. The fundamental was 270 Hz. So 3 times 270 gives us an answer of 810 Hz. That's just 1 mark there. There it is on the marking instructions. That's quite a big question. It covers waves and stationary waves and travelling waves. But let's have a look at another one. Let's have a look at the 2022 paper, and this is question 11. So a travelling wave is represented by the equation y equals 12.6 sine 2 pi 1.32t minus 1.04x. And notice this time the 2 pi is outside the brackets. And in part A, we're told the energy of the wave is 8.17 millijoules, and the wave is reflected and the amplitude halves. And in part 1, we have to calculate the energy of the reflected wave. Well, the initial amplitude of the given wave is 12.6, because the general equation for a travelling wave is y equals a sine 2 pi ft minus x over lambda. So the amplitude A is 12.6. Now the energy of a wave varies directly with the amplitude squared. So if we substitute in for the initial energy and the initial amplitude and square it, then we can work out what the new energy will be based on the fact that the amplitude will have halved. So let's sub in those numbers then. The initial energy was 8.17 times 10 to the minus 3 joules, divided by the initial amplitude, which is 12.6. And don't forget to square that. And then that will be equal to our new energy divided by half the amplitude, which is 6.3. And don't forget to square it. And then if we rearrange that and find E2, then it will be 8.17 times 10 to the minus 3 times 6.3 squared divided by 12.6 squared. And if you do that in your calculator, you'll get an answer of 2.04 times 10 to the minus 3 joules. Now a quicker way of doing that, and you would still get the marks, is by saying that if the amplitude is halved, then the energy will be 1 over 2 squared times smaller, so that's a quarter of its original value. Gives you the same answer, 2.04 millijoules. In part 2, state the equation that represents this reflected wave. Well, if the amplitude's halved, it'll be y equals 6.3 sine 2 pi, and the original wave was 1.32 t. That'll be the same, but it'll be plus 1.04x. Because the wave's moving in the opposite direction, so the minus sign changes to a plus sign. And there's the marking instructions. First mark for all the numerical values, and the second mark for the change of sign. Moving on then, 11 part B. A graph of another travelling wave at one instant in time is shown in figure 11a. And 2 points, A and B, are shown on that graph, and those 2 points are 1.6 metres apart. And we've to determine the phase difference between points A and B. Now, phase difference is a measure of how much they are out of sync with each other, and there's a relationship for that on your relationship sheet. It's phi equals 2 pi x over lambda, where lambda is the wavelength of the wave. So if we substitute in the separation of the 2 points along the x-axis, that was 1.6 metres, and the wavelength of the wave, which we can measure horizontally from the origin, it's 4 metres. And you do that on your calculator, you'll get an answer of 4 pi over 5 radians. Now you can leave your answer like that, because there's exactly 2 pi radians in one wavelength of the wave, so it's okay to leave your answer in terms of a fraction of pi radians. If you would rather convert it into a decimal, you can do that as well, and that's 2.5 radians. But phase angle or phase difference can be left as a fraction of pi. In fact, if we look at the marking instructions for 11 part B, then the answer is given as 4 pi over 5 radians. That was a much smaller question, but similar in terms of being asked to do some calculations using the travelling wave equation. That's it for this video. Next time we're going to have a look at interference. So that might be division of wavefront, division of amplitude, or thin film interference. Might be a monster, but see you in the next one.